Alright guys, so this is going to be another visual to kind of help you out. We're still working on the disk method, and we've been revolving these rectangles around the x-axis. And now for this video, we're going to look at what happens when we revolve it around the y-axis. So instead of going around the x, I'm going to be going around this y-axis right there, that thing. So let me kind of show you what this looks like. You see the rectangle on the screen there. I'm going to hit the revolve button here, and you can watch it spin around. And again, it does what it did in the last video when we went around the x-axis. It makes a disc when it circles. So you can see that disc pretty clearly. And I'm going to break it up here. Here, let's stop this from revolving. Just like we were doing with the x-axis, we can find the volume of this disk. So I'm going to write on the screen here for a moment. If I want the volume of a disk, I'm going to write volume of a disk. Then I know I take the area of the disk, so I use pi r squared. So I'm going to write pi r squared. And then I times it by the thickness of the disk, which we've been calling the width of the disk. And that gives me the volume. So you can see pretty clearly on the screen here that the radius is this portion right here. So here's my radius. And that my thickness, well, kind of depends. Like, this is my thickness. If you can see that little notch right there, it's this little portion on the side here. So the skinnier and skinnier we make these discs, the thickness gets less and less, and our answer gets better. So let me show you a problem. Let's cancel out of this screen here for a moment. And let's look at an actual graph. Make up a different situation here. Okay, so here's our graph. We have a y equals x cubed graph. And we have this blue region from A to B that I'm going to spin around the y-axis. So watch this. Let's spin this thing. There it goes. See kind of what happens is this object forms, and we want to find the volume of this object. That's what we want to be able to do. So you can see inside that purple disc, I can sweep the disc and you can see like it'll start from the bottom here, and these are all the discs being stacked up that we're going to find the volume of. Now we can fill it up with as many discs as we want. If we can fit infinitely many discs into this object, we get the best answer. So let's stop this for a second. So here's my idea here. If I want to find the volume of this entire object, that's my problem. So what is the volume of this object, of this whole entire thing? Then what I'm going to do is I'm going to add up a whole bunch of discs from A to B. And I'm going to use an integral to do that. I'm going to say, let's find the integral from A to B. And sorry, that's a really bad looking B. There we go, A to B. And we're going to do pi r squared for the disk, so pi r squared times the width times the thickness. I'm not going to leave my formula like this. I showed you in one of the last videos that I changed this formula around. I don't really like this setup. I don't like writing width, the W, because in reality the width is so skinny that we can't measure it, so we call it delta x. It's infinitely small. I also don't like putting the pi in the integral. I like to erase that and the r squared. I like putting the pi out in front since it's a constant. And I like rewriting the r based on the graph, based on the situation in the picture. Look at where r is in this picture. R is the radius. It's going to go from here to here. Hopefully you can see that red line on the screen. That's my radius. So the radius, you know, it's short at the bottom, and as the disk goes up, it gets bigger. It's determined by this function, this thing. This is what's determining the radius. So we got to use f of x to figure out the radius. The only complication is if I write f of x in here and use that as my radius, we spun this thing around the y-axis. So I'm not really being accurate. When I'm spinning around the y-axis down here, I need to be using y for my variable. So I need to modify this problem again. I put dx as the thickness. That was kind of a lie. I'm using the y-axis, so I'm going to change all this. I'm going to say that instead of f of x, I'm going to use f of y to be my radius, and I'm going to square it because it's radius squared. And then my thickness is going to be called delta y, or dy. So basically, if I go around the y-axis, I change all the variables to y's instead of x's. Here's how you do that. If you're like, well, how do I do that? If this function on the graph is y equals x cubed, then to get the radius to switch the values, what I'm going to have to do is I'm going to have to solve for x. So I'm going to cube root both sides of this equation and get x equals cube root of y, or I could say y to the 1/3 power. So my radius, this r, that you can see on the screen, is y to the 1/3 power. So the integral setup here is going to be volume equals pi integral a to b. A and b will be any numbers that we choose for a problem. And then my radius is going to be y to the 1/3 power squared, radius squared, times dy, the infinitely small thickness. And so that's our formula. And if I have numbers for a and b, if I decide I want to find the volume from 0 to 7, 0 to 10, whatever numbers I pick, I'll put those into my bounds and I'll solve my integral, just like I would any other integral. So I guess the big note here is that we now have kind of two situations. We have disks that go around the y-axis, and if it circles around the y-axis, then the integral must be all in terms of y. So integral in terms of y. If I do like we did the other day in the last video, if I'm spinning around the x-axis, if I'm going this direction, then my integral will be in terms of x's. So integral is in terms of x's. I'll write that on here. Integral in terms of x's, of x. So you just got to pay attention to your story problems. You got to read them carefully. If it says revolve it around the x-axis, use your x variables. And if it says revolve it around your y-axis, use your y variables. And you kind of get an idea for this. All right, hope that helps. Another video is coming out shortly.